This is active filter design, lecture 28. In the last class, we were discussing the issue of common mode feedback and how one might actually implement it. And our transconductor was a simple differential pair whose job is to convert this difference in voltages VCM plus VD and VCM minus VD into differential currents. All right, and the basic idea was to measure the output common mode, compare it with a reference, and then tweak this potential in the right direction so that the average value of the output voltages remains equal to the common mode reference. And one way of doing the servo amplifier is to use a differential pair which detects the difference between the output common mode which occurs at this node, right, and call this say 2I1, and then which side must the mirror go? Has to be either right or left. Which one is it? Left. Okay. And then which is the common mode feedback node? The one on the right. So okay. And we went over this whole loop, why this is required and how one comes up with this loop and so on in fair amount of detail in the last class. And as you can see, there are at these nodes there is going to be capacitance. What are those capacitances? What are these capacitances? These are the filtering capacitances which are form the GMC integrator, correct? And they are going to be there no matter what, because you want to make a filter in the first place. Okay, this loop is supposed to be active only for common mode signals, and as you can see, these are intentional capacitances for differential operation. But every other node in the common mode feedback loop has its own parasitic capacitances. So everywhere you see a node, a reasonable thing to say is to simply add a parasitic capacitance. Now let's be a little optimistic and say, hey, this node, let's assume somehow that the parasitic capacitance is very, very small, right? So that whatever happens here, right, if the common mode changes, this output voltage, the common mode detector output voltage changes instantaneously. This is the best you can do. You understand? You cannot have the common mode output, you shouldn't have the common mode detector output change before the input common mode changes, right? The people start moving only when there is input applied, right? Only the exception being Madras traffic lights, where even 4 seconds before the red turns to green, people start moving. You understand? That can't happen in a circuit. All right. So we'll assume that the transfer function, the common mode transfer function of the detector is, if these two move up, this moves up instantaneously. Okay, and there is bound to be a parasitic capacitance at this node, right, which is thankfully the same as that node, correct? You understand? And let's again be somewhat generous and say this node capacitance is very small. Okay, from earlier classes you should recognize that that's a reasonable assumption. Okay. Now, why have I suddenly started talking about capacitances? This is after all a negative feedback system, right? Presumably with a lot of gain, okay, and therefore stability is a potential concern, and stability analysis begins with locating all possible parasitic poles and then doing loop gain analysis and the usual stuff, right? So, I have indicated the capacitances, intentional and unintentional, which can come about in such a loop, correct? Now, since we are interested in only the stability of the common mode feedback loop, we know that this loop does not exist for differential mode signals. So, in other words, if the differential mode signals do not matter, I can analyze the whole loop with any one particular differential mode signal, right? And the easiest value of the differential mode signal to choose is 0, right? So, this is the loop for, this is as good a schematic to analyze as any, right, as far as the stability of the common mode feedback loop is concerned, correct? Now, if you look at the integrator part, that is this character, there is symmetry obviously because the gates are connected to the same voltage, the PMOS load transistors gates are connected to the same voltage and so on. So, it does not make sense to work with both halves. I can combine both halves into one and then do the analysis on that section. So, let me do that. When I do that, all that means is that I can work with collapsing both into one circuit or work with one half of the original circuit, it does not matter. I will just choose, that is what I was saying, I could either chop off half the circuit or combine both halves into one, okay. I simply do this, okay. If I combine both halves into one, what will be this capacitance? It will be 2C1, let me call that C1, C1 being the integrating capacitance to ground that we had in the differential part of the circuit, okay. It is understood that the size of this transistor is doubled when compared to each arm of the differential pair, correct. And what can you say about the size of this transistor? This is also doubled, correct. Since there is no harm in moving this capacitor here, I am just going to denote the parasitic capacitance of this guy by Cp1. Alright. Now, the common mode detector is detecting the change in the common mode, right. So, what can I replace it by? Both arms of the common mode detector, both inputs of the common mode detector change by the same amount, correct, and the output of the common mode detector is the average of the two inputs. So, very good, I can simply replace the common mode detector by a short circuit. Yes, okay. So, what once another suggestion is that you can actually replace it by a voltage controlled voltage source, okay, assuming you have buffers. I mean, we saw that one of the common mode detectors we analyzed was a source follower. You can replace it by a buffer, right. This is fine enough, and the justification for this is, even if you have a common mode detector whose input impedance is not infinity but a pure capacitance, correct, then there is no real problem because that capacitance can be thought of as a part of CI. Okay, so as far as the analysis is concerned, it does not make any difference. Alright. Now, does this ring a bell? Does the schematics look familiar at all? Pardon? It is a standard two-stage op amp. Okay, and where are the two stages? Pardon my ignorance. Okay, so which is the first? I mean, the two-stage op amp that you learnt in basic classes. Which is the which would represent the input stage of that op amp? This is the differential pair. Okay, and the output of the differential pair is getting amplified by. In a two-stage op amp with an NMOS input differential pair, the output of the differential pair is getting amplified by a second stage common source amplifier, right? Okay, which is loaded with an active load, which is a current source. Okay, and now which is the second stage common source PMOS amplifier? There is only one PMOS device, so this better be the second stage common source amplifier. Which is the current source active? Which is the active load device? Okay, this is a current source. Hey, but you have a current source and you have a transistor sticking on top of the current source. What's that transistor doing? What does it? Does it do anything to the current source or what? I mean, understand, or we all understand that this is a current source. What is this guy doing on top of the current source? It is a. I mean, it's a. I mean, you can think of this as a common gate amplifier, which is basically doing is a current controlled current source. So the incremental impedance, the output impedance of this transistor is getting multiplied by the GMRO of this transistor. Okay. So in effect, this is an even better current source than this current source. Is that clear? Okay. So I'm going to ask you one more question. What is this guy doing? So if this wasn't around, I would agree that this is the two-stage op amp that you have seen. This is the VCM out, okay, or the detector output. Okay. So if that connection between this point and this point wasn't there, then I would agree that this node, I mean, this represents a two-stage op amp that you're all familiar with, correct? And which is the output of the op amp? Across C1. All right. And but now what we have is we do have a connection between VCM out and the voltage across C1. So what is this doing? This, in other words, this represents an op amp. Okay. All right. Let me change the orientation like this, pointing towards the left. Which is the positive terminal of the op amp and which is the negative terminal of the op amp? Vref is the positive terminal of the op amp. Okay. All right. And which is the negative terminal? The other one, VCM out. Okay. And this connection here, what is it? I need to connect this to, oh, I'm sorry, oops. Okay. Does it make sense? So we see that the common mode feedback loop that we arrived at is nothing but a two-stage. I mean, it's as far as the stability aspects are concerned, it is pretty much the same as a two-stage op amp. Correct? That you are very familiar with. Okay. Now, this two-stage op amp, can you recall what are all the problems with it? As it stands now, please look at this. If this was indeed an ideal op amp, then what is this saying? The incremental change at VCM out is, this is a feedback system, correct? Which is the input to this feedback system and which is the output of the feedback system? Vref is the input, VCM out is the output. So, if I have a feedback loop set up like this, what can we say about the DC value of VCM out? The DC value of VCM out is the same as Vref. Incremental change in VCM out is the same as the incremental change in VCM, in Vref. Okay. And what is the incremental change in Vref? 0, because you're connected it to a reference voltage, which means that the incremental change in the common mode output voltage is also 0, right? Which is equivalent to saying that the output common mode voltage is held at Vref provided the op amp is doing its job properly. Is this clear? Okay. But unfortunately, the op amp that we have is not really ideal. Okay. There is the first stage whose output has a parasitic capacitance Cp1, okay, and there is a second stage whose output, as far as this loop is concerned, has a parasitic capacitance at 2C1. You understand? Is this clear? As far as the common mode feedback loop is concerned, this 2C1 is what you call, it's actually not a good thing because it introduces a pole or more intuitively a delay in the feedback loop. Is that clear? Okay. Now, if we just close the loop like this and then we let it run, what do you think will happen? What is the problem with this feedback network, if any? Okay, how do you figure out the stability? Okay, if you don't want to use Nyquist plots, an easier thing is to use this loop gain analysis. Okay, you break the loop at some point. I decide to break it I break the loop here, which is equivalent to saying I break the loop here and I measure the loop gain. Okay, what do you expect? This is a second order system. Okay, so what do you expect if I didn't do anything? What would I expect for the closed loop poles? Okay, let's quickly write down the expression for the loop gain. What would be the voltage gain from here to here? Let me call this GM say 1. I'll call this GM2. Okay, all right. So if I apply a differential voltage between VCM between these two nodes, what will be the differential current flowing here? It will be GM1 times VD, or let me not call it VD, let me call this delta V just to, or let me call this delta VCM. Okay. All right. Delta VCM represents the error between the desired common mode voltage and the actual common mode voltage. So the current flowing here is GM1 times delta VCM. What happens? So what will be this voltage across CP1? So the voltage across this thing will be GM1 divided by SCP1, okay, times what? Times delta VCM, okay, times, that's this voltage across CP1. What will be the voltage here due to a change in the voltage across CP1? Into GM2 by C1. Correct? 2C, sorry, yeah. Pardon? No, because if I apply a differential voltage across, the question was, by the way, should this be GM times GM1 times delta VCM or 2 GM1 times delta VCM? Why? Why? Yeah, so if I apply a differential voltage delta VCM between VCM out and Vref, the actual voltage across the transistor incrementally is only half that. So the current, incremental current in each of the drains will be GM1 times delta VCM by 2. You are adding both of these currents, so you get back GM1 times delta VCM. Is that clear? Okay, great. So if I cut the loop and apply a delta VCM here, what comes back here is in the opposite direction. Okay. Okay, that's good because we want negative feedback, and it has got a transfer function like this. So this is nothing but the loop gain function. Okay. So if the loop gain, please note where the open loop poles are. Where are the open loop poles? Both the open loop poles are in the origin, are at the origin. Okay. You understand? So now if I close the loop, what do you think will happen to the poles? They will be on the, this is the, in other words, the loop gain as a function of S is of the form GM1 GM2 by S square times CP1 times 2C1. Correct? So the poles of the closed loop common mode feedback loop system will be, the poles will be the roots of the equation 1 plus loop gain. Okay. And the loop gain is of the form 1 by S square. So 1 plus loop gain will have both poles on the j omega axis. So if both the poles are on the j omega axis, can you comment on the quality factor of the closed loop system? The closed loop system has quality factor of infinity. You can also see that in another way. And now that you are familiar with filters, right? The loop gain being of the form 1 by S square means that how many integrators are in the loop? There are 2 integrators in the loop. Okay. And what am I doing now? What I am doing, the loop is doing is multiplying this by -1 and then adding it back here. Correct? This is what? This is the block diagram of we have seen this before in the context of GMC. If you think of a GMC biquad where the input is being set to 0 and the damping transconductor is not there, then what do you have? You have 2 integrators in a loop, okay, with negative feedback. Okay, one is GM flowing into a C, the other one is a minus GM sensing this voltage and feeding it back into the input of the other transconductor. So whenever you have 2 integrators in a feedback loop, what does it mean? If you have 2 integrators in a feedback loop, then it's bad news. Okay, the loop is, for all practical purposes, unstable. You understand? And that's pretty much what you're seeing here. You see one integration from here to here another integration from here to here, and you're closing the, all right. So this is a general principle to be borne in mind. The moment you have two integrators in a negative feedback loop without any damping whatsoever, the closed loop poles will be on the j omega axis, so the closed loop quality factor will be infinite, which is therefore not a, which means the system is on the verge of instability. In practice, of course, you might say no transistor has got an infinite output impedance, so there will be a large resistor here in parallel. There will be another large resistor here in parallel. You understand? What do you think will happen to the quality factor now? Yeah, so you can say, you can argue that the system is not really unstable, but the quality factor will be so high that the what do you call, the loop is, the transient response of the loop will have a lot of ringing, which means that the loop is, for all practical purposes, not very useful. Is this clear? Okay, now that we know what the problem is, we have to figure out a solution, right? So what do you think we can do to fix the problem? Okay, you have to introduce a damping factor, that's sure, but can you think of what do you call, this, let's try and approach this from an angle that you've already seen, right? We can go back to the damping factor example after this, but we saw this in EC201, right? If you have a two-stage op amp and attempt to close the loop, the closed loop poles will have very high quality factor, and therefore the op amp is not as useful as such. So what did we do to fix the stability? We used pole splitting, or we used compensation. And what kind of compensation have you seen before? Miller. Okay. So what did you do in the Miller compensating? We put a capacitor between the output of the first stage and the output of the second stage, right? I'm not going to go through the entire theory of Miller compensation again. If you've forgotten, please refer back to the old video lectures, and you should be back on track. Okay, so looking back from prior experience, we know that if you have a system like this, it's unstable. To fix it, you need to add a compensating capacitor, right? And the best place to add the compensating capacitor is between the output of the first stage and the output of the digression in a Miller. So let me. In that course, this is how the diagrams were drawn. Okay, this was the uncompensated two-stage op amp. So what do you do to compensate it? What do you do for Miller compensation? Put a capacitor between which node and which node? This node and this node. You understand? Okay, so we do the same thing here. So between which two nodes do I need to put the compensating capacitance? between the gate. I'm going to get rid of all this graffiti. All right, so I'm going to add between the input, output of the first stage, or the input of the second stage and the output of the second stage. So I can draw it in many ways. One way is to do this. Okay, let me call this CC. CC is the capacitor that compensates which part of the loop, which loop? The common mode feedback loop. Please note that CC has got nothing whatsoever to do with the differential mode part of the loop. All this discussion pertains to only the common mode feedback loop. Okay, all right. Now, the CC is the Miller compensating capacitance. Okay. This is the Miller compensating capacitance for the two-stage op-amp like structure that occurs in the common mode feedback loop. All right, and of course, one needs to figure out where to put this in the real circuit. Please note that this is only the equivalent for common mode signals. This is not the real circuit. Okay, the real circuit looks slightly different. There is a common mode detector and all this other stuff. We need to figure out how one would like to put CC in order that it appears like this in the common mode equivalent circuit. Is this clear? Okay. All right. Before we get to that, what is the unity gain feedback? Or what is the unity gain bandwidth of this op amp once you put CC? The unity gain bandwidth of this op amp, the moment you put CC, right, is GM1 by CC, provided, because assuming the second pole is far away, which means that CC must be large enough to begin with. Is this clear? People, especially the BTechs who are not very familiar with this, not yet very familiar with this, should please go through the EC201 lectures again, right, and get your your funda straight. All right. So, if CC is chosen to be reasonably large, then the second pole will be somewhat far away from the unity gain frequency, and the unity gain frequency will be at GM1 by CC. And what is the intuition behind the unity gain frequency being GM1 by CC? So, let's say this is GM1 and this is CC. What is the intuition behind? Pardon? Approximating what with what? Yes. No, that's okay. But what is the intuition? Looking at the schematic, what is the intuition that the unity gain bandwidth of the op amp is GM1 by CC? Yeah, so what? No, even if CC doesn't appear as a short, as long as this transistor is an infinite input impedance, right, all this current will flow through CC. So what? Is connected? Yeah, okay. So, as long as if this transconductance, if this GM is very large, right, then this can be thought of as, what is that incremental voltage? Is very small, right. So, all the current GM1 times VD flows through CC. So, the voltage across CC is GM1 times VD by SC, but the voltage across the capacitor is not the output voltage. The output voltage is this node voltage minus the drop across the capacitor. So, if the voltage at the input of the second stage is very small, which will happen when the GM of the second stage is very large, then the output voltage will be simply the voltage across the capacitor, which is nothing but GM1 by Cc. Does it make sense? Okay. Please, this is all background material and you are supposed to know all this. Okay. And where do you think the second pole will lie? Where is the second pole? Approximately GM2 divided by there is no R02, R02 is infinite. It's Cc, no, it's not Cc plus 2C1 plus Cp1, okay, plus 2C1 times Cp1 by Cc, right? But Cp1 will be very small compared to Cc, and therefore that term can be neglected, right? So an approximate value for the second pole is Gm2 divided by 2C1 plus Cp1. Okay. All right, you guys should be very thorough with two-stage op-amp without all the stuttering and not being very confident of what the second pole is and what its values and all that. Okay, it's been done in an earlier course, and in principle you should know it. There's really nothing else I can do other than say this, right? It's been explained to death before, correct? And all I can say is go and watch the videos. There's nothing else I can do. There's no more intuition to give. Okay. All right. Okay. So if the second pole is very far away from the unity gain bandwidth, what happens to the phase margin? What happens to the closed loop Q? Q will come down. Right. On the other hand, if the second pole starts moving towards the unity gain bandwidth, what will happen? The closed loop poles quality factor, the closed loop poles will start to move towards the j omega axis, causing the quality factor of the closed loop poles to increase, which in the time domain translates to increased ringing in the transient response. Okay. So, without knowing any of the formulas, let's say you randomly chose some Cc and you found that it's ringing too much. What is the conclusion and what will you do to fix it? One thing you can do is it basically means that the second pole is too close to the unity gain bandwidth. You can fix this in two ways. One, you either push the second pole out or move the first pole in. Okay. Pushing the second pole out basically means that you would either increase GM2, right, which you may not want to do simply because it's already been designed. Okay, now you have to change currents and all that stuff. Changing current will affect the differential part of the circuit. All right. So pushing the second pole out is not particularly it can be done, but is not a straightforward thing to do. On the other hand, pulling you can always screw somebody up, right? So pulling things down is so easy. Okay. So how do you pull things down? You have to pull. You can either reduce GM1 or reduce or increase Cc. Correct? Either of which is a practical thing to do. You understand? If you don't want to bother with changing, any of the bias currents and transistor sizes, the easiest thing is to increase Cc. Now, if you increase Cc, in other words, if you have increased the phase margin of the loop, what by pulling the first pole down or bringing the unity gain bandwidth down, and what can you expect for the loop speed? The closed loop bandwidth must reduce, because that's the price you're paying for improved stability or improved phase margin or reduced quality factor of the closed loop. Is this clear? Okay. On the other hand, you pull, let's say you put some Cc and the step response is very nice, very sluggish and no overshoot, and it's doing its thing, very slowly. Then what does this mean? This means that the system is overcompensated, right, and is exhibiting typically first order behavior, and you can definitely do with more speed always. So what do? I reduce Cc, and then you will find that the kind of exponential kind of behavior starts to reduce, and suddenly you start to see slight amount of ringing. Okay. And the slight amount of ringing is also accompanied by a reduction in the rise time, because the bandwidth of the loop has become higher. So you can go on tweaking Cc until you see perhaps one ring or so corresponding to a closed loop quality factor of 1. Is that clear? Of course, you can also do the math. You calculate second pole, first pole, and do all this stuff, right? Or if you're one of those types, who doesn't like to do the math and doesn't mind running the simulator a couple of more times, you choose some Cc, right? And this is what is intelligent design, right? It's like, okay, you go and calculate all the parasitics and go blue in the face. Or you run a simulation, you look at it, this is ringing too much. It means Cc is too little, increase Cc. Okay, now if I find that, it's now too sluggish and become too slow, then I choose some value in between and, live with it. You understand? Okay. So, this is basically applying what you have learnt in earlier classes to the somewhat new situation. It's not really new, because it's the same thing all over again in a different form. You understand? And all it takes to design a good common mode feedback loop is knowing how to design a single stage, a single-ended two-stage op-amp, as you've seen here. Okay. Now, so what remains to be done is, we want Cc to appear in the common mode equivalent circuit in this way. Correct? The question is, where do we put it in the real schematic? Okay, so to figure out where to put it in the real schematic, we actually need to draw the real schematic. Yes. Okay. So one question that comes up is, sure enough, you have two gains. Here you seem to have a lot of DC gain, right? Because the gain of each stage, the DC gain of each stage is in principle infinity. Correct? You have two stages of gain. One is through the error amplifier. The other one is the common mode half of the circuit. Because if I yank this node up by a little bit, the common mode output will go down by how much? What is the steady state output voltage? Common mode change? If I change the gate voltage of the PMOS current sources by a small amount delta V, right, and if I measure the steady state change in the common mode output voltage, what will be that change when the loop is cut open? Very high, actually, infinite, correct? Because if the PMOS current pushing down is not the same as the NMOS current pulling, PMOS current pushing up is not the same as the NMOS current pulling down, net charge keeps accumulating on that node and then pushes it, either plus infinity or minus. Okay. Similarly, this stage, okay, the error amplifier also in principle got a very high gain. All right. Now, the question is, why do you need the error amplifier to have a very high gain? The argument is, let me, rephrase this argument in a clearer manner. His argument was, hey, as long as this gain is infinite, right? In other words, even if this voltage is an error by an infinitesimally small amount, then the PMOS current will be infinitesimally off from the NMOS current, but that should be enough to go and push the voltage at the gate by the right amount. The only way this loop can be in steady state is when the PMOS current is exactly equal to the NMOS current. So, in principle, why do you need to have a high gain here? Correct? Okay. A finite gain, no, I mean, you don't need to have an infinite gain, a finite gain would do as well. You understand the argument? Okay. Because please note that steady state error in a control system is basically only depends on, that's what we were taught, right? Depends on the DC loop gain, right? If there is already one infinity, it doesn't seem to make sense to have. Okay. So, the answer to that is, yeah, somebody had a question here. Yeah, okay. So, we need the high gain because of the following. Please note that this voltage, okay, all right, what is the, if this had a finite gain, if this amplifier had a finite gain A, what is this voltage? Whatever voltage is required to give that, whatever voltage is needed to give to result in the proper current in the PMOS transistor. Now, this voltage is what? The difference between those two voltages is what is required to have produce the appropriate voltage at the output of this error amplifier. So, if the gain of the amplifier is small, it requires a larger difference between these two nodes in order to maintain the same voltage at the output. You understand? So, if you do not have very large gain, then there will be a small error between the output detected common mode output and the VCM reference. You understand? That error will become smaller and smaller as this gain becomes large. Correct? Okay. Now, but still, this is a valid point. You can still have, you can have finite gain. Okay. In fact, you can have a reasonably low gain if you design the device sizes properly. You can end up with a fairly robust design. So, the argument is not what do you call incorrect by any stretch of the imagination. It's perfectly fine. And in fact, you see many designs where, as we discussed, we said that this looks like two integrators in a loop. To stabilize two integrators in a loop, you need to damp one of the integrators or damp both integrators. Correct? So, one way of damping, there are two integrators. If you are only interested in damping one integrator, there are two ways of doing it. You can damp the first integrator or you can damp the second integrator. So, in other words, I can put a resistor across at the output of the first integrator, or I can put a resistor across the output of the second integrator. So, in other words, instead of having CC, I can have resistor across CP1 or a resistor across 2C1. Where would you think you would put the resistor? You can put across CP1, or why not put across C1? I mean, anything you do across C1 will also affect the differential mode. So, people, what you want to do is to put the resistor across the CP1, and an easy way of accomplishing that is to simply not worry about getting an infinite gain. But do this instead. Okay. So, now which integrator is being damped? This integrator is now being damped because the load is now is of the form 1 by Gn, right? So the DC gain is not infinite, and therefore depending on how you choose the geometry of the transistor, you will be able to get the Q that you want. All right. So this is also a way of doing it. However, as I discussed before, the finite gain will usually cause an error between Vref and VCM out. Okay. All right. Now the next question is to figure out how one might implement the CC such that it appears, like a Miller capacitor in the common mode equivalent. And for that, let's get back to our original circuit. This is the differential pair. All right. Let me take a simple example of a common mode detector, perhaps. Okay, we can assume ideal buffers at this point. Okay, this is the transconductor with common mode feedback, right? This is the common mode detector. Okay, please recall that in the in the common mode equivalent, we decided to put the Miller capacitor between the output of the first stage and the output of the second stage. This was CC. The question is, what should I do here? The output of the first stage of the common mode feedback loop, that is this character, is well defined. There is no ambiguity at all. Correct? So this is one plate of the compensating capacitor. Now, what do you think we can do? What all do you think we can do as far as the other plate of the compensating capacitor is concerned? This is C1. Pardon? Okay. Okay, so that's fair enough. Here's one suggestion which works in principle. CC by 2, CC by 2. Okay. What do we notice here? In the differential mode equivalent, in the common mode equivalent circuit, this node and this node are the same. So, as we wanted, CC appears between the output of the first stage and the output of the second stage. All right, this is a valid suggestion. Now, the question is this a good suggestion or is this a bad suggestion? What are the problems with this?
No, the CC, the first stage of the common mode output for differential, it is ground only.
Yes, so I mean, pardon, yeah, this node you mean?
This node is differential, for differential circuit is ground.
Correct.
So CC by 2 will
Okay, very good. Okay, so we also see that this is not particularly a great thing to do, because this node, what is it for differential equal signals? What is the gate of the PMOS transistors as far as differential mode is concerned? So connecting CC by 2 between the output nodes and the gate of the PMOS transistors is something which would indeed compensate the common mode feedback loop in principle, but it has the practical difficulty that CC by 2 now appears in parallel with C1 in the differential mode part of the circuit, right. I mean, this is not a particularly desirable thing, okay, and so is often avoided.
Oh, can we, in that case, I can reduce C1 if I know what is the compensation capacitance. I can reduce.
Yeah. So what the argument being made is that if I know C1 by 2, if I know CC by 2, I can reduce, instead of having C1, I can have C1 minus CC by 2. The problem with that argument is that typically the CC you would like to realize using MOS capacitors, for example, because linearity of these capacitors is not an issue at all. On the other hand, the integrating capacitors better be linear capacitors. What is a linear capacitor and what is a non-linear capacitor? What is the difference between the two? In other words, in a linear capacitor, the charge is a linear function of Q is equal to CV, right? So in other words, Q is a function of V, where that function is a straight line. In a non-linear capacitor, what happens? Q is a function of V, where f of V is some kind of nonlinearity. Okay, so if those of you who undergone a devices class will know that a MOS capacitor is all sorts of funky behavior, right? Whereas a parallel plate metal capacitor has got Q versus V, which is a straight line. Okay, but what is the advantage of MOS capacitors over MOS capacitors are formed with gate oxide, which is perhaps the thinnest dielectric on an IC. So you can make a large amount of capacitance in a small area. Unfortunately, the capacitance will be nonlinear, right? So if you can live with a nonlinear capacitor, then it always makes sense to use a MOS capacitor. If you need linear capacitors, then you have to use metal plate capacitors.
How did we come up with the factor timing? It doesn't matter if the capacitor is nonlinear.
Well, as far as differentials, see, our output is simply the difference between these two voltages, isn't it? The integrator output is simply the difference between these two voltages. Okay. Now, if these guys happen to be nonlinear, then the voltage across them will not be a linear function of the current that is pumped into them, correct? Imagine that the whole of C1 and the CC by 2 are made with nonlinear capacitors, then the voltage is clearly not linear with respect to the pumped current differentially, correct? So clearly, as far as differential operation is concerned, you want the integrating capacitance to be perfectly linear. As far as common mode is concerned, it doesn't matter, because the two ends of the capacitor are both incrementally grounded for differential mode signals. You understand? If the capacitance doesn't even appear in the differential mode equivalent, then whether it's linear or non-linear is hardly an issue. You understand? So the compensating capacitor in the common mode feedback circuit need not be linear, right? Whereas the integrating capacitors better be linear if you want a linear filter. Is this clear? Okay. So therefore, the practical reason is that CC by 2 is typically made using MOS capacitors, which are nonlinear, in order to save space. So you don't want part of, you could in principle reduce C1 by this amount CC by 2, but now we have part of a capacitance which varies one way with temperature, and you have another part of the capacitance which varies some other way with temperature. Managing all this is a pain, right? Apart from the nonlinearity problem. So this is definitely not something that you would normally do. Okay. All right. So this is a feasible solution, but is not quite as good as we would want. Okay. Next thing. Any other suggestion? So as far as common mode signals, please recall that these two nodes are equivalent, and so are, so is that. So what one might want to do is to put the capacitor here. Okay. Does it make sense? So you can go on, a little bit of thought will show you that this is exactly equivalent to putting CC between the output of the first stage and the output of the second stage in the common mode equivalent circuit. Okay, and often you can also it's also drawn. Okay. Pardon? No, not quite. Come again.
As earlier we did, we clubbed them together.
Yes.
So output of that is going to a that R parallel R and then this.
Yes.
That resistance will.
Yeah, the resistance now enters the common mode feedback circuit. That's a valid point. Okay, this is something that, for example, let me call this Rx and this also Rx. So what is the equivalent common mode circuit right now? Common mode feedback equivalent. So I'll just go back to this part. Where is the common mode equivalent? There will be a buffer here. This is the equivalent of the common mode detector. Okay. All right. Yeah, sure. Rx by 2. Okay. So this will indeed affect the behavior of the feedback loop. You can go and do the math yourselves. But what do you think as engineers without doing the math? Do you think small Rx is good or large Rx is good? No, as good engineers, do you think small Rx is good or large Rx is good? Large Rx here, a large resistor in series means what is it doing, guys? Whenever you have a large resistor in series, it's making things slower, correct? Which means that whatever, how many ever poles are there, some poles are coming. So always putting a large resistor in series where there was none before is bound to make things slower, which is bound to make feedback loops less stable, right? And so on. You understand? So without doing the math, I'd be willing to bet that Rx is detrimental to the operation of the loop. It indeed turns out so. But so that's why you cannot choose any arbitrarily large Rx that you want. You understand? In fact, it also turns out that another parasitic capacitance we neglected is the input capacitance of the error amplifier. Okay, this has got a more direct. This impact can be seen, even without CC. If these two jump up, okay, what happens to the voltage across this capacitance? It will move slowly, right? There will be a delay between the detected common mode and the actual input common mode to the detector. This directly comes in the loop gain as an extra pole, and what do you call, makes stability a problem, or reduces the phase margin of the common mode feedback loop. Okay, so again, a common fix for this is, you want why would you want to use large Rx? Now what output stage?
Tolerance will be due to temperature changes.
buffer will give less current.
If negative feedback loop fixes the voltage and the output of the integrator, then the value of Rx will come in parallel.
Look carefully. The Rx is just a part of the common mode detector, right? What kind of common mode detector did you see last time? What were the buffers that you used? Voltage controlled voltage sources, right? So if you want linear voltage at the sources, please note that if you use the common drain amplifiers for the buffers, then what you are actually averaging is not the outputs themselves, but those voltages which have been already processed by the common drain stages. You understand? Okay. What are these two voltages? VCM? Yeah, blah blah blah, that's correct. Okay, so what you're technically averaging here are the outputs of are not these outputs, but the voltages at the sources. When is the voltage at the source? And I mean, the incremental voltage at the source will be the same as the incremental voltage at the gate only when GMRX is very very large. Okay, so which is why you want to make Rx large. But if you make Rx large, what happens? It will introduce extra poles in the feedback loop, common mode feedback loop. You understand? So there is a reason for making Rx large, right? But if you make Rx large, stability gets screwed up. So how do you want to? I mean, how can you use a large Rx but ensure stability?
Put a cap in parallel with that.
Yeah. So what you can do? I mean, the problem with a large Rx is that when I yank what happens to that voltage? It rises slowly. Okay, understand? Okay. Now if Rx wasn't there, but this was, if I simply had a capacitance, what do you think will happen? It will stay instantaneously, but with what amplitude? The step, it will rise quickly, but with a reduced amplitude. Correct? So now if I put Rx in and there's a parallel capacitor here, what do you think will happen? It's a combination of the two. So you will get some jump and then a slow rise to the top. Do you understand? See, negative feedback loops start becoming unstable when you yank one side of the loop and nothing seems to be happening at the other end. Right? Then what does the poor loop do? Go on increasing, right? And then the output comes like 6 months later with all the force that has accumulated over the last 6 months, and then it's like by that time this guy has probably gone nuts. You understand? So that's why in a feedback loop you must have a fast path which gives you some indication of whether you're doing things right or wrong. All right. I mean, the example I like to give is, whether you want to turn. See, if there was a switchboard and I asked you to turn on or turn off the light, you can do it very quickly. Why? If you turn it off, you see immediately either the light goes off or not. If the light goes off, it's the right switch. Otherwise, it's the wrong switch. You move on to the next one. But if a fan was running, right, and if I gave you the same job of finding the right switch which turns off the fan, now it's a lot more frustrating because you turn the what do you call the switch off, correct? Or even if the right switch, the fan doesn't seem to be. I mean, it's very difficult to detect the change in the velocity of the fan. So you don't know whether you've done it right or wrong. Okay. So, you will do this and then nothing changes and you think you've done wrong and then you go, turn it back and then go to the next switch and all this stuff. And if, if you're impatient, you will basically never be able to turn off the fan. Correct? You understand? That's because there's so much delay in the feedback loop that, and you have so much gain. Gain is basically impatience. Correct? So, if you see some small difference, you want to get this thing, working, that's what a fast amplifier is. A slow amplifier is one which, waits and then waits and then waits and goes, have a cup of coffee and come back and see if the fan, right? You could do that. You switch off some switch, you go have a cup of tea, come back. If the fan is still on, you made the wrong switch. You switch something else off, you go have another cup of tea and come back, right? So, that's in other words, you are the dominant pole in the loop. It's not the fan. You understand? So, there can only be one dominant pole in the loop. Alright? Whereas when there was a light, it is infinitely quick. The moment you turn on or turn off the switch, the light will go off. So, the only dominant pole in the loop is you because you are the slowest part of the loop. You understand? So, the same way, if you have so much delay in the loop because of the RC network, the loop will go unstable.
Sir, you said that we want Rx to be large for the voltage buffer part, but the voltage buffer means the GMR or the GMR is only for the differential.
Correct. For the differential one.
How does it affect the common?
No. See, as far as if this capacitance is, in the earlier analysis we had neglected this capacitance. Okay. So, now in practice, if you got too greedy and made Rx too large, right? Rx times Cp by 2 or whatever, is the time constant associated with charging of that capacitor. That introduces extra phase and delay and makes life miserable. Okay. So, what you need to do therefore is to have a fast path, which may not be very accurate, right, but does give some indication of, give the feedback loop some indication of whether it's doing the right thing or not, and that is done by putting a capacitor in parallel with Rx. And what happens? The moment the input common mode changes, alright, the output will jump up by a fraction of the input jump depending on the ratio between C and whatever C1, okay, and then the last bit of settling will happen through the resistor. In feedback loop parlance, you are actually adding a 0 of transmission, right, and this is what enhances the stability of the loop. Okay, so
you are only saying that Rx should be smaller, so we can make Rx smaller. I didn't understand why Rx should.
No, you wanted to make okay, all right. So let me get back to this. Of course, you would we would, as far as stability of the loop is concerned, you want Rx to be small. But as far as this is concerned, as far as the common mode detector itself is concerned, please note that you are averaging the source voltages of these.
That is dependent only on the quiescent.
Correct. So, if you want this source voltage to be an accurate reflection of the gate voltage as far as the incremental signal is concerned, okay, then you want the GM of this guy times Rx to be much larger than 1. Correct? Only then that will be a good buffer. Now, if you want GM Rx to be much larger than 1, what is the easiest lazy man's way out? You can either increase GM or increase Rx. I would go and sit and increase Rx simply because it requires no effort, right? Because no quiescent current flows through these guys anyway, I just simply increase Rx. But the moment I do that, the stability of the common mode feedback loop is compromised. So, it's not a, if I just chose an arbitrarily large Rx, that would make destabilize my common mode feedback loop. So, I must add these capacitors across the resistors. Is this clear? Okay. So, Okay, so now let me quickly draw an entire schematic. Okay. So this is the complete, what you call dot zero version of a voltage controlled, fully differential voltage controlled current source. This is the current mirror which sets the bias tail currents for all the transistors, for all the differential pairs. Okay. Understand? Okay. So which is the differential part of the circuit? This part. Okay. Which is the common mode detector? Which is the error amplifier? This correct. Okay. Which is the common mode reference generating part? Okay. You understand? And though the circuit looks quite complicated, you know that it's not really that complicated. Okay. All right. So this is when somebody draws a transconductor and says GM. Okay. What is meant is all this. All this must be there inside. Okay. Or some equivalent form. And one straightforward thing you can do is keep, as I indicated to you before, keep these current sources fixed and apply the common mode feedback where? To the tail current here. You just have to flip everything, upside down. Especially in the error amplifier, you need to now make it a PMOS error amplifier and all that stuff. I mean, it's quite straightforward. Maybe, if you guys want to think about just strengthen your intuition, you may want to just attempt to draw the circuit diagram of something like that. Okay. We will find that, okay, as far as common mode, this is, what you call, again, as I said, a dot zero version where the output common mode remains at a reference value that we'd like. Okay. And the differential output current is GM times the differential input voltage. Okay. Unfortunately, there are several problems with several non-idealities associated with the differential part, which we'll need to fix. The first one, of course, is finite output impedance. Okay, and we'll also have to see, as I promised you earlier, transconductors are noisy. Okay, and we said that the noise is of the form some 4 eta kt times gm. We'll have to evaluate what that eta is for this particular animal. Okay, and then we have issues like finite output impedance and all this other stuff. One thing that we have avoided so far is to talk about linearity at all. Correct. So clearly, if Vd becomes too high, then we know that the output differential current cannot exceed the tail current. So we have a problem. So we'll have to understand linear range of the transconductor, noise, output impedance, and what we can do to fix these problems. Okay. From now on, I'm not going to sit and redraw the common mode feedback circuit for every little transconductor that we do. I'm just going to concentrate on the differential part, and at some place I'm going to say VCMFB. That's assumed to be coming from some arrangement of transistors like this, which detects the common mode, compares it against the reference, and goes and generates the appropriate common mode feedback voltage to regulate the output common mode. Okay, and the stability of that you can analyze using the same techniques that we have followed so far. Okay, so I will stop with this. We continue.